So in this video, we're going to talk about initial theta data. So in particular, we're going to talk about the existence of this technical condition. So existence of initial theta data. In particular, the local global compatibility, and then we're going to do this. Then we're going to do initial theta data in a particular example. Okay. So let's fix k. So let me say that that what we're going to do is can be found in Silverman. Let's say this is the advanced topics book in chapter 5, section 6.2. So this is just in the chapter on complete curves. Okay, so we're going to take k over q to be a number field. So this is what we're going to fix. E over k, an elliptic curve. And then we're going to suppose that the J invariant is not integral, so it doesn't have potentially good reduction everywhere. And so there's this. And so for all but finitely many L prime. So this is a rational prime. There exists a basis of EL K bar such that and some let's say sigma in GK such that so here sigma L of sigma is equal to 1101, where this L is the mod L representation. And so this is, of course, written with respect to the basis. EL K bar. Okay, so this is the lemma. It says that this condition that we needed will work for all but final. So there's going to be some sigma here, so that this this thing works. Shit. Okay. Okay, so let's give a proof of this. So proof. So we're going to fix a finite place. Some place with the norm of the J invariant here, where this is positive. Okay, with respect to this element. Okay, and so we'll fix an embedding of K bar into the completion here, the algebraic closure of the completion, and so we have a decomposition group here, GW. So this is the absolute Galois group of the local field, and this will be inside the absolute Galois group of the field. Okay, so so by the existence of local transvections, so by existence of local transvections, so there's some sigma in the local Galois group, and PW1, 2 points, PW2, L torsion points, okay, such that here rho, so this mod L representation, but the local version of sigma is equal to 1101. Okay, so this is of course relative to the basis. PW1, PW2 basis. Okay, so so the identification. So notice that these things here. So the identification. It's just really simple. So it uses the fact that here. So we have dw here inside gk, and that the fact that the algebraic torsion here. So like that torsion is algebraic, really. Okay, so the torsion is, this gives the result. Okay, so that's the point, is that really these things are really global bases. Okay, so now we're going to give an explicit example of initial theta data, or an explicit elliptic curve. Okay, so now we're going to give an example of an elliptic curve. Sitting inside initial theta data. So let's do the example. And then the example that I want, so maybe we can keep kind of a running tab of the things that we need to define. So here, let me write down the tuple of initial theta data. E, F, M, here. Okay, so this is what we're going to have. The elliptic curve that we're going to start with is E. So this is the E11A1, or we'll just call this E11. So it has a minimal Weierstrass model. So this is the one. This is the Cremona label here. And so this is y squared plus y. So this is, I'm writing down its minimal Weierstrass model right now. And there's a couple facts about it. So it's J invariant. So it's J invariant of E11. So this is negative 2 to the 12th, 11 to the minus 5, times 31 cubed. It has the only place of bad reduction is 11. So then this allows us to specify that. So here again, you can already see that the field F mod here for this example is Q E11. This is just Q. Okay, and so this tells us that we can take, well, the only choice really is VBAD mod, so this needs to be the set 11, like so. Okay. So that's, sorry, that this is not supposed to be underlined. It's just a VBAD mod there. Okay, so it turns out that the tape parameter here for this particular place at 11. So it looks like 10. I'm just going to write out the first couple of terms. 11 to the 5th plus 2 times 11 to the 6th plus 6 times 11 to the 7th plus 6 times. So 6 times. So let's see. 10, 2, 6, 6. 6 times 11 to the 8th, I believe. Let me just double check this real quick. yeah, and then plus 5 times 11 to the 9th, etc. Okay. So so what we can do is we can pick L is equal to 13. This will be admissible. So to do this, we really need to know what F is. So so we need to check this conditions against F. So F is going to be so F is obtained by making torsion extensions. So the orders of these subgroups are going to divide of R. They're going to divide GL2 of FR. So this is R squared minus 1 times R squared minus 1 minus R minus 1. So this will have, so when R is equal to 2, this will be 3. So this one's equal to 6, which is just equal to 2 times 3. And this is 48, which is equal to 2 to the 4th times 3. So what we need, okay, so the prime L is going to be prime to the degree of all these extensions, which is nice, which is something that we need. And so the order of Q, so this is 5, so L is coprime to 5, and the order of all these things in 11. Okay, so that gives us what L is. We also have what F is. F is obtained in this way. So epsilon and so okay, so we fix an algebraic closure. We're not going to bother with that. I mean, you just fix your favorite algebraic closure. We're going to have to fix a set of lifts of places. This won't matter so much. But now we can specify, okay, we've specified the elliptic curve over F. The elliptic curve is given by this thing. And then we just need to specify these two pieces of data. And so what we can do is, we'll use that decomposition that we had before. And so what we'll do is we'll use, so I guess I can write it here. So, so this thing is going to be Q to the 11 over 113. And so since this is a generator of that, 1 over 13 here. Okay, so we're using the decomposition as before. And we'll get this. And then this will induce a global group here. So that gives us both of those pieces of initial theta data. So this is enough to give us initial theta data for this particular example. Okay, and so some of the cases that we'll want to consider are the case, like kind of the full case where we take all the primes of band reduction. But two cases to think about when we're doing these is with the case when F mod is Galois. That's a nice case. And then the other nice case is that when this thing is a single prime, like we're doing right now, V bad mod, right? So when this is a single prime, then this thing will simplify our weights considerably, and this thing will this will also simplify the computations considerably. Okay, that's how to produce an example. This is one example of initial theta data for yeah. So I just wanted to be like a little bit more explicit with this description. So in terms of the previous videos, so where we wrote this basis out, so we're if phi 11 is this map from Q11 bar cross to Q11 here, so this is the Tate uniformization, EQ11 Q11 bar, so this is the Tate curve, and so this is isomorphic to EQ11, the algebraic closure here. So this is our E11. So this is our curve right here. This is the Tate curve with our Tate parameter. So we're going to write this whole composition to be this. So this is the Tate uniformization. So P11 1. So this is phi 11. So I wanted to write this as algebraic points p11, 2. This is phi 11 of q11 to the 1/13th. Okay, this is for the 13 torsion. And so this induces, so this map here to L torsion, so we can have, so this is a 13th root of unity here, q to the z over, so q is this thing, this is q, q to the 11th z like this is phi 11 EQ11, so this is our particular guy that we've been talking about. Okay, and so this is one way where if we use the Tate for uniformization that we can produce these algebraic points. So by construction, I just want to say that P11(1) and P11(2), these are algebraic points. And the class of P11(2) is equal to the class of epsilon, where this thing here is going to be contained in this particular curve, or this particular L torsion subgroup. Okay, so so the other thing to say is that this p-adic canonical splitting induces the splitting globally. Okay, so given the local splitting, we get a global splitting. Okay, and so we get, the other thing is that we get, the other thing that we use is that we'll have something that's algebraic over the completion, that's really algebraic over the global field, right? So that's the other thing that I wanted to say. And that's all I have to say about that.